Good afternoon, ladies and gentlemen. Welcome to today's webinar. Today, we're going to talk about an image structure that is designed to measure the temperature of the objects in a microwave cavity. And we're gonna do this design using the do of SolidWorks and HFWorks. The agenda of the webinar today is going to be an introduction and the objectives of the electromagnetic bandgap structure. Then we're going to see the software in action, and at the end we're going to have a question and answer session. So, as I mentioned, today we're going to talk about the structure that help us monitoring the temperature in a microwave cavity, because objects in the microwave cavity are being heated using the microwave radiation. However, we know that microwave cavities can create hot spots and cool spots. So when we are heating something in the microwave, if we want to be able to monitor the status of the object, especially when we are using industrial microwave devices, it's important to find a way to measure the temperature contactless, because we're not going to be able to use thermocouples as the microwave is going to damage the thermocouple inside. So the best way is to use an IR sensor. Infrared sensors are based on thermopiles, of course. And thermopiles measure the temperature by seeing the modes of heat loss through the objects inside the cavity. However, in order to be able to measure the temperature, they should see the object. As you see, there is a requirement for the view angle for the thermopiles. Thermopiles, in order to be able to measure it correctly, should not be disturbed by the noise created by the microwave from the cavity. And we know that if there is holes in the cavity, the microwave is going to leak, and this leakage will compromise the accuracy of the measured temperature. So we are going to introduce a small filter that can be placed between the microwave cavity and the thermopile. This high power filter will filter out the microwave frequencies. For example, in this case, the microwave that we're dealing with is operating at 2.45 gigahertz. While it has a big enough opening that meets the angle requirement of the thermopile, so it can still see the object and can still grab the modes of the heat loss from the object. We're going to do this using the do of HFWorks and SolidWorks. So I'm sure that all of you are familiar with SolidWorks, which is the most powerful CAD in the market, and over 10 million users are using SolidWorks on a daily basis. So HFWorks is a full three-dimensional electromagnetic field simulator which is fully embedded inside SolidWorks. So HFWorks is a gold certified software by SolidWorks, and it can handle electrothermal simulation, high power, high frequency simulations like S parameters, antennas, resonance, and it can use the SolidWorks and the multi-core features of your devices. So now let's try to see the software in action. You're all, as I said, familiar with SolidWorks. So we have created this object with SolidWorks CAD. As you see, this filter is designed to be fabricated with aluminum or copper later on. As you see, it's kind of a periodic structure, image structure. So it's like a circular waveguide, small circular waveguide loaded with some irises inside, as you see. So the dimension of this is the outer diameter of this waveguide is about a centimeter, and the inner diameter of the iris is 6.3 millimeters. This 6.3 millimeters of opening will guarantee that there is big enough, that this opening is big enough to see the radiation from the infrared radiation from the object inside the microwave cavity. So how to simulate it? Of course, when we're running a high frequency simulation using this finite element software, we need to mesh the path of the radiation. So how do we show the path of the radiation? The radiation is going through the air. So we need to try to create the air that the wave is passing through. So in order to do that, I have created an air box. I'm gonna show it now. Here is the air box that we imagine one side of this air box is where the objects inside the microwave cavity are, and the other side of this air box is the place that we place our thermopile. So we want to see how much radiation can pass through this side of the air box to the other side. So between the two, this filter stays. So let me hide this filter for a moment. If I hide it, you see the air in between looks like this, because those irises that are loaded inside this circular cavity, circular waveguide, create these artifacts in the air between the two places. So how do I model the wave between these two locations? Because one of them, the microwave, exists in one of them. The other one is the place outside the microwave cavity that I'm trying to read the temperature over there. My thermopile goes to the other side. So here, in 3 simple steps, I can define my study. First of all, as you see, HFWorks is just another tab inside SolidWorks. So just by clicking on HF, I'm inside my HFWorks. So I need to define a study first. How do I define a study? I just right click and say study. So I have 3 different types of analysis here. I can have a parameter study, I can have a resonance study, and I can have an antennas study. Then I have the choice between using a direct solver or an iterative solver, and in each of them I can use the multi-core option. So for this one, I'm going to use a multi-core direct solver. We also have the normal accuracy and the higher accuracy. The normal accuracy uses the zero order element of the mesh, and the high accuracy uses the higher order elements, like first order or second order elements. We have the option to parameterize our study, and then we do have the option of discrete sweep and the fast sweep. So what is the difference? In the discrete sweep, all the full dimensional problem will be solved for all frequency points, while in the fast sweep, an expansion point will be considered in the middle of the frequency band. The full problem will be solved there, and then estimation using the model order reduction will be done for the rest of the band. So we'll have a kind of an estimation for the rest of the band to give us an idea, so we know where to go from there, how to tune our design. So for example, in this one, my concern is the 2.45 gigahertz, where the home microwaves work, and like many industrial microwaves, the ones that use 2.45 gigahertz magnetrons, of course. So let's say I want to monitor the effectiveness of this filter between 1 gigahertz and 5 gigahertz. And I want to see, like, let's say 100 frequency points in between. So it automatically decided that it's going to use 3 as the expansion point. And actually, I can increase the number of expansion points to increase the accuracy of my fast sweep. We do have the option to compute TDR. Of course, this is good for some circuit simulations and traces and these things, but we do have the option of computing TDR also in the software. So I defined my study. Then I need to do 3 pre-processing steps. First, I need to define my material. I have two bodies, like 2 parts. One part is the air that I created just to mesh and model. The other part is the RF trap itself, like I called RF trap here, is the filter. So you can come here because I hid it, so you can show it again. This is our filter, right? So in this study, my filter or trap is going to be metal. So I can use copper, or I can apply PEC, like perfect electric conductor. So in this case, I think we can apply copper. PEC, perfect electric conductor, or copper. Let's say PEC. And for the air, I go to the favorite material and choose air. As you see, I'm not limited to these favorite materials. I can go to the apply material, and we have a big library of all kind of materials, like all kind of cables you see here, all kind of ceramics, all kind of semiconductors, all kind of substrates, everything. I can choose, and you see when you come here, you see all the properties of these materials are there. So you can choose the material of any of your parts over here. So here it was easy. You had air and PEC only. Then I need to define my boundary conditions. In this case, the boundary condition, I need to have a port here, right? First, I'm gonna define this side as a port, because this is the side that we're gonna use the excitation. So we have microwave present inside this box. Then I will define another port on the other side to read that port, because then we're gonna do this S analysis to see how much of the power excited by this port is going to be delivered to the second port, which is the observation port. And at the same time, we need to make sure that we apply PEC boundary condition on the bodies all around to make sure that our housing is complete, and we can also do our port calculations here. The third and last step of the pre-processing is to mesh our structure. So I can mesh it as simple as that. I create mesh and start to mesh. So it can start to mesh automatically itself. Okay, so it will give me a preliminary mesh. And I will take a look. If it seems fine enough to me, I will start to run my simulation. Look at in the meshing, when we did create mesh, even there is an option to run analysis after meshing. It means this is the last step before running your analysis. But if I felt that the mesh is a little bit coarse and it might not give me the accuracy that I'm expecting, I can always refine my mesh in two ways. One way is when in the create the mesh, I can actually simply turn this bar towards fine, so it will give me a finer mesh. Or if I just want a finer mesh on a certain part or on a certain surface, I will simply apply mesh control. In the mesh control, I can say only on this part, or no, only on this surface, or even no, I can even try to say only on this edge. Give me a finer mesh. This way, I can make sure that I will have more elements in, for example, sharp edges where there is a possibility of the singularity of the field or anything, and where there is smoothness and I don't need so many elements, I will leave it coarse so I can have a faster computation. So over here, and then after I did that, I can simply go to the study and say run. So I ran the study like right before this presentation. So this is, let me hide this metal part again. So let me show you my mesh. This is my mesh that I had applied. So I made sure that there are enough elements, especially in the areas like in the ports, which need more elements for the accuracy. And over here in the irises and everything, I applied some mesh control, as you see over here, to make sure that I do have enough elements. And then I ran the study. So after I ran the study, the results came up. So in the results, I can see the electric field, the three-dimensional, the electric field, magnetic field, the port field, and then I can see my result table. Look at all the frequency points. Plus, I can plot the speed chart, any 2D plot that I want. For example, I say I want to look at S11. So I add my look, S11, S12, whatever one. I want to see S11 versus S12. I can even do two plots at the same time. So show me the result. As you see here, my S11 is almost 0 dB. It means that I will have no power can pass through this. Everything is going to be reflected back. That's what I wanted, because I didn't want any microwave to pass through this structure. And you see S12 is like minus 200. So all the power, like no power is going from port 1 to port 2. Everything is going to be reflected back inside the cavity. So of course you see we have all kind of features to improve the look of the curves here. If you want, like, you can change the style of the line to dashed line, dot line, solid line. You can you have a marker, change the marker sign. If you want to make for example, the line thickness, you want to make it thicker. I'm working on the red line now. I make it thicker just to be more visible. So we have all kind of options in the post-processing part, which is plotting our data. Or if, for example, I wanted to look at my Smith chart, of course, I want to look at my S11. There you go. You see, it's far over there, my Smith chart. So I can make it like thicker, just to take a look at the results. Then at the same time, let me hide the mesh here. You might want to take a look at the electric field. Say, okay, I just say I can have a 3D fringe plot, I can have a 3D vector plot. Let's have a 3D fringe plot without any clipping. Oh, there you go. Here we can see how would the electric field look like. And not only I can see that, I can try to animate it. I can animate it to, I'm animating it versus phase to see how would it look like. You see the movement of the field, but you see nothing will passes through this middle part to get to the other side. So it means we furnished our goal here to filter out the microwave on one side. I can, at the same time, if I want to have a better grasp, I can do clipping. I can do, for example, section clipping here. By section clipping, look, I can have it at any cross section that I want. I can clip it like at this structure, at this cross section if you want, or at this cross section. As simple as that. And I can move, you see, I can move my cross section to see what's going on at any face. At the same time, I can do iso clipping to show the field in iso surfaces. And by moving this bar right and left, I can alternate my iso surfaces. I can make it inside out if I want. See? Simple as that. So, and as I said, we can also see the port fields if we're interested. We can also, for example, in this one, let's try to look at the vector plot. So, electric field plot of the port. See, here is the vector plot. So, one other neat feature that we have in the software is that it will give us the result table, complete result table for all kind of parameters, and you can export it, of course, in Excel or anything that we need for our future references. And not only that, we can ask the software to create a report for us. You can ask it to generate a report right here. For example, in either Microsoft Word or HTML format. And if you want, you can have a cover page, introduction, any of them. You can check or uncheck to include in your report. Let's say we want HTML, or we want Microsoft Word. So, and we just say, click generate a report. Look, as I said, we can write an introduction ourselves. For example, we say webinar on December 7th, 2007. Okay, so description, everything we can add, and then, okay. It will generate a report automatically based on the 3D model, on the results that we were interested in, on the plots that we plotted, and everything. And look, it opened the Microsoft Word right here inside SolidWorks for me to show me, look, this is what we added. And There's the file information. Here's the file information. Here are different angles, different views of the model. And then we have the results in the result table. As I said, we can customize it the way that we want. We can include it, exclude it, or we can add more details if we want. And also, at the end, look, you can go all the way down. You see all the plots that I did look at them, they are all appearing here. So I think we have covered most of the material that I wanted to tell you about this filter design and also about the features of the software. So this actually, just to let you know, this filter that we designed here, we also fabricated it and we tested it on a microwave acid digestion device, and it successfully worked. And it's actually being used right now on commercial products just to help with the temperature measurement without any noise. And at the end, I would like to thank you very much for your attention. Unfortunately, we will not have time to take any questions, but please email me at alex@emworks.com if you had any questions, or if you wanted to ask for a quote or a trial version for the software, the HFWorks inside SolidWorks. I will be more than happy to help you with that. Thank you very, very much for your attention. Enjoy the rest of the evening. Have a nice day. Bye.